Hello again. So in this question, we will have again a joint probability density function that belongs to two random variables, x and y. However, there is a tricky part in this question. As you can see, the domain that these random variables are defined are dependent on each other. For example, it says the random variable x can take any value between 0 and 1, but for a specific value of the first random variable, the second random variable y can only take a lesser value than it. Again, the lower bound is 0. However, it says the random variable y can never be greater than random variable x. So first, the realization of the first random variable occurs. The first random variable can take any value between 0 and 1. However, given the value of the first random variable, the second random variable can only take values between 0 and that realization of the first random variable. Therefore, the possible domains of these random variables are dependent on each other. However, you can easily realize it from here that the second random variable y can also take values between 0 and 1. For example, if the first random variable x takes the value of 1, then the second random variable can also take any value between 0 and 1. So it is also possible for the second random variable to take any value between 0 and 1. In fact, instead of defining the boundaries of these random variables, the possible values of these random variables like this, we could have also used another way of doing it. So we could have just said that the second random variable y can take any value between 0 and 1. The second random variable y can take any value between 0 and 1. And because the possible values of x should be greater than y, we can also say that the first random variable x can take values between y and 1. So this expression here and that expression you can see here are the same expression. So they are defining the same solution sets. All right, so in this question, it says we need to compute the marginal PDF of X and marginal PDF of Y, and we are going to do that. Now you see the joint probability density function over this domain is equal to 8 times X times Y. So it's not a linear function this time because we are multiplying the two variables here. But one thing we need to be careful here is the possible values of a random variable is bounded by the realization of the other random variable. So which one is realized first is defining the boundaries for the second variable, okay? So we should not say that the possible values of y is defined by the value of x, the vice versa. The opposite is also true. The possible values of x is also defined by the possible values of y. Now, if we intend to draw this function 8 times x times y, you will see that it is going to have a shape like this. As you can see in the region, in the unit square, in the region where y is taking greater values than x, the PDF is equal to 0. So you see this 8 times x times y is only defined, it is only defined in the region where x is greater than y in the unit square, and that function is equal to 8 times x times y. And in fact, neither x nor y can take any other value outside the unit interval. So only this triangular region on the two-dimensional domain is defining the possible values of random variables x and random variable y. All right, so we are going to calculate the marginal PDF of x, the marginal PDF of x in the first place as a part, asked in the first part. So we are going to do that. What we need to do is, if we are going to calculate the marginal PDF of x, we need to integrate the joint PDF over the y variable. We are going to squeeze the joint PDF through the y variable. So the integral operator will be dy. However, because of this definition, because the random variable, second random variable y can only take values between 0 and x, we need to integrate the joint PDF from 0 to x with respect to y operator. So y is the reason for that. So let me just show you this over the two-dimensional domain once again. So let's just say we have these two random variables. The first random variable can take any value from 0 and 1. And the second random variable can also take any value from 0 and 1. Okay, so this is y, this is x. The possible values that these random variables can take are in which region? Let's show that. Let's show the possible values these random variables can take. Now you see y can never be greater than x. Therefore, the possible values these random variables can take are within this region only. Okay, and over the third dimension, as you can see in this picture, there is a joint probability density function. Now, at this point, it is not important. We are going to calculate the marginal PDF of x at any point x. So we are interested in calculating the marginal PDF of x at any point x here. So we need to integrate the joint PDF through this line. So from 0 to x. So we need to integrate the joint PDF from 0 to x, because for a specific value of x, the possible values of y are defined between 0 and x. And in fact, you can see it here as well. It is indicated here. The possible values of y are defined between 0 and x. Therefore, the integral is supposed to be calculated between 0 and x. And when this integrand is integrated with respect to y, it will become 4x times y squared. Plugging in the x and 0 values, you will get 4x to the power 3 as the marginal PDF of x. And because x can take any value between 0 and 1, we are going to say that this PDF is defined within this region. Now, coming for part B, remember now, even though in this representation it is told that y can only take values between 0 and 1, x, because the maximum possible value of x is 1, it is also possible for y to take the value of 1 as well. Therefore, theoretically speaking, we need to state that the random variable y can also take any value between 0 and 1. But it depends on the realization of x, just like the realization of x depends on the realization of y. Now, you can also see this here. Instead of that representation, we could have defined this domain of these two random variables in this manner, and you can see that y can take values between 0 and 1. However, the possible values of x can take are between y and 1. Now, this time we are going to calculate the marginal PDF of y, which requires the integration of the joint PDF over the x variable, right? Now, this time, let's just say we are interested in the marginal PDF of a specific value of y between 0 and 1. Then we need to integrate the joint PDF from this point to this point. Now, because over this x equal to y line, the value here is equal to y, we need to integrate the x variable from y to 1. Therefore, in the second part where we intend to calculate the marginal PDF of y, we need to integrate the joint PDF with respect to x operator. Remember, if you're interested in the marginal PDF of a random variable, you need to integrate the bivariate joint PDF over other variable. And the other variable can possibly take values between y and 1, because as you can see here, x can never be less than y. Okay, for a specific value of y, the possible values of x are defined between y and 1. Therefore, the integral here will be the integral of 8xy with respect to x, 4x squared times y, and plugging in the x values as 1 and y and subtracting from each other, you will get the result of the marginal PDF of y, which is 4y minus 4y to the power 3. Now, let's just look at the plot diagrams of these marginal PDFs. Now you see what we are doing basically in calculating the marginal PDFs is for random variable x, we are squeezing the joint PDF over the y variable. So from this direction to this direction, we are squeezing, we are toasting the three-dimensional function into 2 dimensions. And in that squeeze, what you are going to get will be this. Okay. Now, on the other way, if you are going to calculate the marginal PDF of y, then you are going to squeeze the PDF in this direction over the x direction, right? And in that case, the marginal PDF will look like this. Okay. So for both of these random variables, we can calculate the marginal PDFs. Now, of course, the marginal PDFs are different here. Why? Because even though the contributions of x and y are the same into this function, their domains are dependent on each other. Okay, they are not the same. For example, if x takes the value of 0.5, then y can only take values between 0 and 0.5. Okay, so the possible values that they take are dependent on each other. Therefore, even though the contributions in the function are the same, the marginal PDFs will never be the same. Therefore, if as a continuation of this question, if somebody asks you what is the expected value of random variable x or the expected value of random variable y, you need to answer them separately by calculating the expectations with respect to each marginal probability density function.